Assalamualaikum warahmatullahi wabarakatuh, and good day everybody. So now we are moved to our new chapter in dynamics. Basically in our syllabus we have learned until now is a 9 chapter. Now this chapter is chapter number 10 in our syllabus, but in referring to our textbook RC Hibler Engineering Mechanics Dynamics, this chapter will be chapter number 3 in your textbook. Okay. So now what we have learned in what we need to learn about today class is for the work of force, the principle of work, energy, and system of particle. So the objective of this lecture, this class is you should be able to calculate the work of force and also apply the principle of work and energy to a particle or system of particles. Okay, another equation for working kinetic problem involving particles can be derived by integrating the equation of motion F is equal to ma with respect to displacement. So if you are integrating this equation with respect to displacement, and then what we have learned in kinematics, we have learned that E tangential acceleration is equal to V dv ds into this equation. So we need to integrate the tangential equation, or the Ft is equal to mat. The result is integrate to yield to get an express or equation known as the principle of work and energy. So we need head here. So we have this path, the curved linear path here. So we have the tangential axis. We have normal axis to the curvature point of curvature for the curve. So we have the normal point. So the force. So the resultant force we have in the resultant force in the tangent component. We have the resultant force in normal component. So the principle is used for solving problem that involve the force, the velocity, and displacement. It can also be used to explore the concept of power. So use the principle, we must first understand how to calculate the work of force. So basically a work does work on the particle when the particle undergoes a displacement along the line of action of the force. So work is defined as a product of force and displacement component acting in the same direction, meaning that the force and displacement must be parallel in the same direction. So if the angle between the force and displacement vector is a theta, but it's not is a theta, so the increment of work du by du done by the force is a du is equal to f ds cos theta. If you are substituting cos theta is cos 90, you will get the 0. So no work for the if the theta is perpendicular. So only up the theta is not the perpendicular to the direction. So by using definition of dot product and integrating, the total work can be written as the total work from the point 1 to 2 is given by the integrating the f vector dot dr from r1 to r2. Okay, so if f is a function of position, a common case, this become u12 is equal to f cos theta ds. So if the both f and theta are constant, so force equal to a constant, this equation further simplify to a force multiplied by cos theta multiplied by distance s2 minus s1. So work is positive if the force and movement are in the same direction. If they are opposing, the work is negative. If the work and displacement direction are perpendicular, the work is 0. As I said 0 because cos 90 become a 0. So if the force is the same direction with the movement, the work become positive. If the force is the opposite direction with movement, this one becomes negative. Okay, work of weight. I think you have learned your physics. Work against gravity. This is just a little bit recap where I have learned the work against gravity. So the work done by the gravitational force acting on the particle or weight of an object can be calculated by, because our direction is a positive upward. So the weight is the gravitational constant is the positive downward. So because of that, you can see here negative because the work is going up is positive. Now it's a negative because the opposing the direction. So we given by the displacement from y1 to y2. So the work done by the weight or the work done by against gravity is a negative w delta y or negative mgh. Okay, as I said just now, if the theta is upward, so the work is negative since the work force always act downward. Okay, work of a spring. When a stretch, a linear elastic spring develop a force of magnitude Fs is to Ks, where K is the spring stiffness and S is the displacement from a stretch spring. So given by here, so if let's say we have the initially S equals 0 here, so let's say the spring is elongate, so the S will be we have the distance, the stretch length that become the final length become larger depending on the force, either compression or tension. So the work done of the spring force moving from S1 to S2 given by, we are need to integrating by Fs ds from S1 to S2. So with the substituting the Fs Ks here, so what we get, the 0.5 K S2 square minus 0.5 K S1 square, or half Ks2 square minus half Ks1 square. So if the particle is attached to a spring here, for example, the force Fs exerted on the particle is opposite to that exerted on the spring. Thus, the work done on the particle by the spring force will be negative, because when the particle is actually particle is attached here, the force exerted on the particle is opposite. Because if you will release the spring will become original become at the initial position. So actually the force is the opposite with our direction of the spring, so that the work done on particle by the spring will become negative, or we just put negative into our equation here. So it's important to note that the following about spring force, the equation both are for linear spring only. Recall that a linear spring develops a force according to F equal to Ks, essentially the equation of 9. So work of spring is not just spring force time distance at some point, but beware, this is a trap that students often fall to, because this one is a F equal to Ks is just force by a spring. So if the work of the spring, we need to use the previous formula, this one. So finally, always double check the sign of spring work after calculating. Is a positive work if the force on the object by the spring and the movement are in the same direction. Okay, by integrating equation, so now we are moved to our principle of work energy. We have done the work done. So the principle of work energy is we need to integrating the equation, the tangential force, resultant tangential force equal to So we are integrating the tangential component equal to MAT. So the principle of work and energy can be written as So we can written as the kinetic energy, initial kinetic energy plus the total work done from point 1 to point 2 equal to final kinetic energy here. So if the total work is done, total resultant U12 is the work done by all forces acting on particle as it move from point 1 to point 2. Work can be either positive or negative. So you need to understand here. So T1 and T2 is the kinetic energy of the particle at initial and final position respectively. Thus T1 is equal to half mv1 square, and also T2 is a half mv2 square. So kinetic energy always positive scalar because the following velocity here square. So for the particles, initial kinetic energy plus the total work done by all the forces acting on the particle as it moves from its initial to final position is equal to the particle's final kinetic energy. So the principle here is not a vector equation, because each term is a scalar value. Both kinetic energy and work done have the same unit of that energy. So in the SI unit, the unit of energy is called joule. 1 joule is equal to 1 Newton dot meter. In the FS system, this one is the imperial units are feet dot pound. The principle of work energy cannot be used in general to determine force that are normal to the path, since these forces do not work. The principle of work energy can be also applied to a system particle by summing the energies of all particles in the system and work due to all forces acting on the system. So we can see here this example. So for example, this object, the body is a slide through the rough surface, rough metal here. So we are applying the external force here. We are taking the pulling force P. Consider a block which are moving over a rough surface. If the applied force P just balance the resultant frictional force mu k, because here we have mu k and a constant velocity would be maintained. So here, what we can see here, the principle of work energy will be applied as a half initial velocity, half mv1 square plus ps. P is a force multiplied by a distance that move from point initial point here to final point here, minus the mu kn. Mu kn is the friction force. So friction force also develop the work done to the object for the object. So friction force multiplied by distance equal to final kinetic energy half mv2 square. So this equation is satisfied if the P is equal to mu kn. However, we know from experience that friction generates heat. A form energy does not seem to be accounted for in this equation. It can be shown that the work term mu kn is represent both an external work of the friction force and internal work that's converted into heat. So we need to find all the total work here. So normal force and weight, it doesn't relate for this our equation, because this one is perpendicular to each other, perpendicular to the motion. So only P and also the friction force. So we need to put into the equation, this one is the initial kinetic energy, this one is the final kinetic energy, this one is the total work done from point 1 to point 2. Okay, I think we stop here in the principal work energy. So we are continuing our session in the next video. Okay, see you, bye bye.